This video is talking about long division and synthetic division. So you saw a video on long division last night. So I'm going through this one pretty quick. But basically, if I divide 2x to the fourth plus 5x squared, or 5x cubed minus 5x minus 2, um, I just used the long division algorithm that we talked about last night. So synthetic division is something that's very similar. So we start with the root that would be associated with x plus 3 that goes in the box. And then all of these numbers are the coefficients of that polynomial 2x to the fourth, and so on. Notice that I put a 0 in the middle. That's because it's missing the x squared term, just like I did in long division. So now what I end up doing is I pull the first number down, then I multiply by the number in the box, and then I add. And then I continue to do this. So I pull the number down so that 2 goes down. Then I multiply by the number in the box. So all of the green highlights are multiplication. And then I add down. So I multiply -3 by 2, and I put a -6 in that next column. I add the columns. And then eventually I get 2, -1, 3, -14, and 40. Notice that those are identical to what I had in the long division. So as you can see, the answer ends up being identical either way. So now the question becomes, how do you do synthetic division? And we'll go over it a little more slowly. There's a video on this that you're going to watch tonight, but we're going to do a little brief introduction today so you can do some problems. Write the coefficients of the terms. Do not forget to put a 0 for missing terms. Write the value of the root of the denominator, which is the same thing as the number that you would be substituting in if you're talking about a substitution problem. Bring the first coefficient down to the bottom row, multiply the bottom row number by the value of the root, put that in the next column, then add the columns and repeat the process. So you already saw this up here, but we will just do this a little bit more. So if I have 2x to the fourth plus 5x cubed minus 5x minus 2, the value of the root of this, if I were dividing by x minus 2, or if I were factoring x minus 2, I would say that it's a root at x equals 2. So because that is the root, that's the number that I'm putting over here. I'm writing this value. Then I write the coefficients of these, 2, 5, 0. Since I'm missing an x squared term, I write a 0x squared. Then -5 and -2. I bring the first coefficient down to the bottom row, and then I multiply, then add. So multiply 2 times 2 and add. Multiply 2 times 9 and add. So 0 plus 18 is 18. 2 times 18 is 36, and add to get 31. 2 times 31 is 62, and I get 60. So since my directions were divide, this down here are the coefficients, the results of the division, just like they were originally when we did this. Notice that these numbers were the same as these numbers. And so basically, since I started with an x to the fourth, I ended up with an x to the third. So I basically reduce the powers by 1, and then I write the result. So the result is 2x to the third plus 9x squared plus 18x plus 31. Then this is my remainder. And anytime you have a remainder, you write the remainder divided by what you were dividing by. So if my directions are divide, this is my answer. Once again, I will do the exact same thing with this same polynomial, except in this case I'm dividing by x plus 1. So my root is x is negative 1. Bring the 2 down, multiply. Bring 5 minus 2 is 3, multiply with negative 1. 0 minus 3 is negative 3, multiply. Add, multiply. Add, and I get 0. So in this case, my remainder was 0. So when I divided, I end up with something that doesn't have a remainder. Now, what does this mean? Well, this means that x plus 1 is a factor of 2x to the fourth plus 5x to the third minus 5x minus 2. Because if something evenly divides it, it's a factor. So what are some other benefits that can come from synthetic division? The remainder when dividing is equal to the value of the numerator polynomial when substituting in the value of the root. So let's talk about what that means in this problem. If I want to substitute x equals 2 into this polynomial, I can plug in 2, get 2 times 2 to the fourth plus 5 times 2 to the third minus 5x minus 2. I'm sorry, x is 2. So I can replace that. And I can do this, and that works out great. But if this number gets bigger, or if these powers get bigger, this gets to be a very long, drawn-out process, especially if you don't have a calculator. Now, I can certainly do this. Like 2 to the fourth is 16 times 2 is 32. 2 to the third is 8 times 5 is 40 minus 10 minus 2. So I end up with 72 minus 12, which is 60. But also notice the remainder when dividing is equal to the value of the numerator polynomial. So notice what we did up here. We divided this by x minus 2, which means it had a root of 2. And so if I did this process right here, what I would end up with is 60. And so I can do the exact same thing and get a value. So since my directions here say the value of the polynomial at a given value of x, if I want to find it at 2, I substitute 2 using synthetic division, but we can also call it synthetic substitution. So instead of writing the polynomial, because the question is not asking about the polynomial now, it's now saying, what is f of 2? Well, it can give me the exact same thing. F of 2 is 60. So if I did f of 5, or I'm sorry, problem 5, f of negative 1, all of this is something that I could just redo over here. And then I find that my value is 0. So f of negative 1 here, if I plugged in negative 1, I'd get 0. So if I ask a different question, I can actually use synthetic division or synthetic substitution for more than just dividing. I can get a value of a function. I can also find finding these zeros can help me factor the polynomial. So what do I notice? If I want to factor this polynomial, which I've already worked with most of this worksheet, what did I see? I saw that x equals -1 is a factor because if I plug in -1, I get 0. So what I can do is I can also say that if I look at my coefficients, remember as I wrote what this was, if I divided by x minus 1, I end up with 2x to the third plus 3x squared minus 3x minus 2. Well, what would happen if I multiplied that by x plus 1? Well, I'd get back what I started, right? Because that's just a property of multiplication and division. If I take this and divide by x plus 1, and I get what I highlighted in green, then if I take what I highlighted in green and multiply by x plus 1, I get back what I started. So if this is a factor, I can then write it like this. So now I can use this to factor this polynomial. And so now I can look at this and say, do I know how to factor this? Well, it doesn't appear it's going to work very well with grouping, so maybe I have to do another synthetic substitution and kind of see what I can do and try and factor it. So I'll use a little bit more synthetic. So 2, 3, -3, -2. Let's see what I can plug in. Well, I could try -1. I could try, I mean, I basically don't know what the answer is yet. And when you do the video tonight, you're going to see me trying some things and failing. But let's just try x minus 1. So if I plug in 1 and I do some multiplying and adding, it does work. I get another root. And so now when I divide 2x cubed minus 3x squared minus 3x minus 2 by x minus 1, I can factor this a little further, and I end up with 2x squared plus 5x plus 2. I can use synthetic even more if I want, but this is something that I'm going to just try and factor using original methods that we've learned since Algebra 1. Like, can I factor 2x squared plus 5x plus 2? Yeah, that's 2x and x plus 2 and plus 1. So I've now fully factored this. My answer is x plus 1, x minus 1, 2x plus 1, x plus 2. And I can, again, write each of these parentheses in any order because that's how multiplication works. So I have fully factored this polynomial. There was no GCF. Now I've fully factored it. Another thing I can do is, so I found zeros that can help me factor the polynomial. So that's what happened here. And then fully factoring can help me solve equations. So if I take a look at this equation and I move everything onto one side, so 2x to the fourth plus 5x cubed, subtract 3x squared from both sides, well, the 3x squareds go away, subtract 7x from both sides, I get minus 5x, and add 4 to both sides, I get minus 2. Oh, hey, look, it's the exact same thing we've been working on the whole time. If I see this, and I've already known that this factors, and I've factored it already, now I can solve this super easily. So I just set all of these things equal to 0. X equals -1, x equals 1, x equals -1/2, and x equals -2 are the 4 answers. Okay, now we're down to the trickiest part of synthetic division. If you are dividing by something with a leading coefficient, you must be very careful because synthetic division or substitution is actually always like dividing by a binomial with a leading coefficient of 1. So I'm going to just talk about this kind of briefly. So I'll use synthetic on this one. So for the first time, I'm not using the exact same problem that I've done in every problem. So given that 5 halves, when I plug that into the function, gives me 0. And so it's telling me to fully factor. Now we really like problems like this that tell us what to use. So when I plug in 5 halves, I know it's going to give me 0. So let's see what happens. 4 times 5 halves is 10. Then I add negative 20 plus 10 is negative 10. Negative 10 times 5 halves is negative 25. And I add and I get negative 6. Negative 6 times 5 halves is negative 15. So as promised, I have a 0. Now what's happening is I've now factored this, but what I've factored it into is x minus 5 halves times 4x squared minus 10x minus 6, which is kind of a weird way to write this. This is kind of strange. So we typically don't write things like that normally. Now notice what happened is that this now has a GCF, and this looks weird with a fraction. And notice what the GCF of this is. GCF of 2. Notice what this would really like. It needs to be multiplied by 2. So take this GCF, pull it out, and multiply this by what was missing. So now I have 2x minus 5, and I pull the GCF out of this, and it's 2x squared minus 5x minus 3. And can I factor that? Yeah. So I can factor this to 2x and x minus 3 plus 1, and I end up with this fully factored.